All right. Good morning, everyone. We can start our lecture on modern control, lecture number 2. Just to remind you what we learned previous time. So we talked about LTI systems, linear time invariant systems. We showed one particular approach to characterize this type of systems using delta response or impulse response. So using impulse response, you can practically draw any signal with multiple deltas in series, and then based on the linearity and based on time invariance, you essentially can compute the output of the system using convolution integral or convolution sum if it is discrete system. All right. Then we talked a little bit about closed loop control, how to compute closed loop transfer function. We talked a little bit about algebra, polynomials, and why we need all of these polynomials, because all of the transfer functions are typically written as one polynomial divided by another polynomial. So it makes sense to know something about polynomials and their roots and how to compute them. And typically we will not go much farther than third order polynomial, third degree polynomial, because computationally it's too difficult to compute it by hand, right? So computer will do that for us. But theory will stay the same for any order polynomials and for any order systems. We will just concentrate on those smaller order polynomials because it's just easier to see how stuff works by hand, okay, just to walk through the process. And then you will just use MATLAB or whatever tool you are using to compute everything you need about roots of the polynomials and factorizations and all other stuff that you need to do in controls typically. All right, so also to remind you, very important theorem by Euler, which is saying that e to the j theta is cosine theta plus j sine theta. And this also means that e to the j theta are points on the unit circle. And this also means that absolute value of e to the j theta is always 1 by definition of what it is. All right? So this is something that we will be using from time to time, so you need to remember that part. And this will explain some parts of the theory, so you need to remember this part from complex numbers and complex functions. All right, so just to remind you something from control theory 1. We have poles and we have zeros in transfer function. So if you have transfer function, which is h of s like here, and you have numerator, denominator, and then this is your transfer function. It's one polynomial divided by another polynomial for any linear system, right? So roots of that polynomial are called zeros, and roots of that thing are called poles. Why is it important to talk about zeros and poles in general? So motivation is very simple. These are practically minima and maxima of the function. So if you think about them as hills and valleys, if I'm giving you points of hills and valleys, you can approximately know how the function looks like, right? So you can, if I give you like minima, maxima points, you can draw some curve between them without knowing exactly how this curve goes. So it could be a little bit different between these points, obviously, but overall shape you can estimate pretty well from these critical points, right? So you can pass some continuous and differentiable curve between them. And this is how typically the responses look like. So you can estimate the responses just based on the zeros and poles without knowing the details what is happening between them. And also they identify that entire thing in only one possible way. So all you need to know is DC gain, which is a coefficient of bn minus 1. And everything else you can identify from the poles and zeros. Because you have factorization of the polynomials, you can factorize each one of these polynomials. Knowing the roots, you know the entire polynomial up to the coefficient, obviously, right? So the only thing you need to know, location of the roots, that coefficient of the gain, and you know the entire transfer function. So this is why it is so important. Now, we also can connect location of the poles, for example, of the system to performance of the system. So it depends on where the poles of the systems are. They could be stable or unstable. They could be fast or slow. They could be with overshoot or without overshoot, with all kind of settling times. And we can even connect that to particular calculations that you are doing in controls 1. But we are not doing that here. I'm just reminding you that all of that is possible. Why I'm talking about that? Because in state space, our goal will be to put poles of the system wherever we want them to be. This is the goal of entire theory here. So instead of like finding border diagrams or all other things and designing based on the border diagrams or root locus or some other tools that you learned in Controls 1, here our goal will be to locate the poles in particular places. And based on that, we will know what performance and stability the system will have in closed loop, right? Just by knowing where the poles are. Yes?
Question. Can you go back real quick?
Sure.
So when you were talking about the zeros are, like, I'm just thinking about in terms of like a polynomial, right? So, if you
So
have
zeros are
poles-
roots of that polynomial numerator.
The minimum and maximum, right? And then the poles are when you have, so it's like, that's when it's horizontally zero, and then the poles are where it's like vertically, like you hit an asymptote or something, right?
No. So like you have two polynomials, one divided by another. The roots of that polynomial are zeros, which means when you have that root, that entire transfer function is zero, which means zero gain, practically speaking. So it's notch filter. So at frequency of the zero, you have notch filter down, band stop. So you're stopping everything which happens at that particular frequency of s equals to j omega. This is zero. So when you have particular zero at particular j omega equals to s, right, at particular omega, then you're practically stopping that entire thing because the entire transfer function is zero. And transfer function is kind of gain, but complex gain, but still gain. If you're thinking about absolute value of the transfer function, it's gain. So if upper polynomial equals to zero, which is zero, right? So zero divided by anything is still zero. So you're practically multiplying that frequency, no matter like what amplitude of that signal is, you're multiplying it by zero. So your output for that frequency will be zero, which means it's notch filter.
I mean, I get what you're saying.
Now, poles is the opposite one, which means if you have root here, right, then you have infinite gain at that frequency. Right. So it's notch the other way or resonance. So this is filter, like if you have that particular frequency, at that frequency, the gain will be infinite.
Right. So I guess what, so we only really are plotting this in like the Bode sense where you're getting zero or pole.
Yes.
Okay. Okay.
I mean, you have also phase, but phase of zero, it doesn't matter, and phase of infinity also doesn't matter. Okay, so here is how we're drawing zeros and poles. This is zero pole map. Let's say you have transfer function like that. You can estimate that in MATLAB, and you can plot that in MATLAB with that function IOPZ map. And this is how it will look like. Again, sometimes we call that axis j omega. Sometimes we call it imaginary. Sometimes we call that axis sigma. Sometimes we call it real axis. Same thing, it's just complex domain, okay? Real and imaginary. But these are kind of frequencies that you have in the system, and these are real parts. And we will see why we use that kind of definition of what it means. Also to remind you that if you have regular polynomial and it has some sort of complex roots, they always be symmetrical regarding the real axis. So you'll have always conjugate poles and zeros. They will come in pairs always. Real ones do not have to come in pairs. You might have them anywhere you want, okay? But pay attention that all of this might be symmetrical regarding the x-axis. Any questions? Yes.
So, in the middle image where you've got R of s equals 1 over s, and then you've got the transfer function, you have y. Why is R of s 1 over s? Does it have to be 1 over s?
This is just step. So Laplace transform of inverse Laplace transform of 1 over s is step function. So typically in control systems, we are using input of step. This is just example. You can use any other input.
So that transfer function can take any input at all?
Any input. Okay, another control design question. So previous time I proposed some silly mechanism to control systems. It was obviously not realistic and not practical. But I have another proposal here. So let's say you want to get output equal to the input, and now I'm not disconnecting the controller, I actually connecting controller, but my controller is 1 divided by your transfer function of your plant. So your plant is g of s, call it h of s, g of s, doesn't matter, some transfer function. And let's say it's ideal, so you do not have any problems or issues with that. And then my controller is 1 divided by g, which means if you multiply this part by this part, you get 1 transfer function, which means that y equals to r again. So the transfer function is 1 closed loop, my closed loop without closed loop. Okay? So what is wrong with that design? Why this would not work in control systems? Why people do not do that? Actually, people do that sometimes, but it's not a great idea. Sometimes you have open loop control like that. You can see some systems like that. But typically people do not do that. Why is that? Isn't that simpler than like designing controllers, closed loops, all of the mess? Is that your type of design? Like, do you buy that? Haven't you seen that in Controls 1? This is a relatively simple question. And you can get, this is not the only one correct answer here. There are like 5 different correct answers here. Why you shouldn't do that. Okay, how about initial conditions? What do you know about initial conditions of g of s, of your plant? This is correct answer, nothing. Okay? You know nothing about your initial conditions of your system, which means that GS is assuming 0 initial conditions, but they are not 0, right? All transfer functions assuming 0 initial conditions, as we discussed previous time. We talked that all of the transfer functions based on 0 initial conditions, but they are really no. You do not have 0 initial conditions. You have some initial conditions, like you have particular angle from which motor starts, right? And you're not really measuring that angle because you do not know that angle, and you cannot really measure that. I mean, you can, but it's too much of a headache. I guess people do not do that. So, what is your initial conditions of your controller then? They need to be exactly the same initial conditions. But they are 0 because you don't know them. Which means that this system starts from completely different initial conditions compared to this system. Right? So you obviously will get mismatch between them. Between what the first system is doing and second system is doing. Even if the GS is the ideal and you know all of the parameters, obviously you have uncertainty in parameters, so you do not know GS exactly up to like 10th decimal point, right? All of the coefficients are approximate, you estimated it somehow. So 1 divided by GS is not exactly inverse of GS, it's approximately. So this will cause all kinds of problems. What if the system is unstable? How about unstable system? And you're putting it in open loop. It will be staying unstable. Why should it become stable if you have something unstable? More than that, if you have unstable zeros in G of S, and then you're inverting it, they become poles. The system becomes unstable, even if it was stable in the first place. Okay? So it's not asymptotically stable anymore. Not stable at all. Okay? What else? You have other things coming in. How about disturbances, noises, and other things like that, which you do not take into account and exist in reality, obviously. But most interesting problem here is something that people never notice, is that typically the system is proper. And by proper, I mean the order of the numerator is smaller or equal to the order of the denominator. Okay? Proper systems are physically realizable. You actually can realize them because they are causal, which means their future depends only on past and present. Like they compute the signal right now based on all of the past signals. Inverse system, which might be the opposite from that, which might not be proper at all, right, needs future values to compute the output. Which means derivative that you use in these transfer functions is not causal function physically. You cannot actually implement it. So you do not have transfer functions where you have more zeros than poles, which is causal, because you need future values to compute the output of the transfer function. So you physically cannot build it. You cannot build that controller if it is that way. So the only way you can use it is only when function is not strictly proper, which means number of zeros equal to number of poles, and then you can invert it. This is the only case where you can use something like that. And people sometimes using that simplistic approach, but this is not great for all of the other reasons that I mentioned. Okay? Any questions? All right, so now we are getting to questions of stability, and these are very important questions for state space as well, because we will convert that type of stability to state space stability, which would be still asymptotic stability, still will be same definitions that you've seen before, but I will connect these two. So I just want to remind you what asymptotic stability is and what BIBO stability is. Bounded input, bounded output stability, BIBO. Okay, so asymptotic stability in terms of that linear transfer functions that you have means that all of the poles are in the left semiplane, which means they have negative real part, all of your poles. This means asymptotically stable. BIBO stable means exactly the same thing, but after cancellation of zeros and poles in the transfer function. So if your system is of particular order n, and you have some poles and zeros cancelled algebraically, like you have like s plus 1 at the top and s plus 1 at the bottom, you can cancel them, right? So if it was stable before cancellation, not stable, if it was all real part negative before cancellation, this is asymptotically stable. If only after cancellation, then it's BIBO stable. So BIBO stability is a weaker property, which means if it is asymptotically stable, it's definitely BIBO stable. But the meaning of these two things is completely different, which is very interesting relation. Because what is the meaning of asymptotic stability and what is the meaning of BIBO stability? BIBO stability means that you have zero initial conditions, like no initial conditions, everything is zero in your transfer function. You put in bounded input and you must receive bounded output. So for any bounded input, you receive bounded output, which means it's not diverging anywhere. It could oscillate, it could do whatever, but it's not going to infinity anywhere. Okay? This is BIBO stability. So again, zero initial conditions, particular input, which is bounded, so not going to infinity, bounded with minimum and maximum. And the output must be bounded if it is BIBO stable. If it is not BIBO stable, it will diverge for particular inputs, okay, or for all inputs. Sometimes for all inputs, sometimes for some inputs, right? So this is not BIBO stable. Asymptotically stable is completely different thing. The input is zero, and it must to converge to zero from any initial conditions. So the meaning of asymptotic stability means that the system is converging from any initial conditions with zero input, and it converges to zero. Because it's a linear system, it has to converge to zero. So completely different things, but same theorem. The only difference is like after cancellation or before cancellation of zeros and poles. That's it, this is the difference. Now, for discrete time systems, which are in Z domain instead of Laplace domain, same thing, but for unit circle instead of left semiplane. So all of the poles need to be in unit circle for discrete systems. Then the system is stable. And again, before cancellation or after cancellation will tell you if it is BIBO stable or asymptotic stable. Questions so far? It's a little bit tricky to remember all of the pairing here, but hopefully I'm just reminding you, and this is not the first time you hear about that. Okay? So here is an example. Let's talk about that example. Let's say you have some transfer function. I already made factorization of both polynomials for convenience. And clearly you can see that s minus 2 is cancelled here, right? And you get simplified transfer function of lower order. So before cancellation, you clearly have -2 here, which means the pole is at +2, s equals to 2. So it's unstable pole, which means the system is not asymptotically stable because the pole is on the right semiplane. But after cancellation, everything is stable. So it is BIBO stable, but not asymptotically stable system. Okay, so for any bounded input, you will receive bounded output. But for particular initial conditions, it might diverge. This is how it works. All right? Questions? Now I will talk about Rawls-Hurwitz criteria for stability, and this is what you learn a lot. You probably spent 1 or 2 weeks on that. Yes.
Can I go back one? So the fact that you have a 0 and a pole at +2, right? Is that kind of saying and the reason it's BIBO stable is because there is a set of initial conditions where it will come to 0, and then there's a different set of initial conditions where it will be unstable.
Not to 0, it will come to something which is bounded.
Sure. Okay, correct. But then the idea is that there exists some initial condition that it will cause.
For which it will diverge, yes.
Right. Because you have it.
Yes, so for 0 initial conditions, it will not diverge
How do you
ever.
draw the Bodhi plot at +2 then? I guess you don't, but it's not real. But.
You don't see anything in body for that. It just cancels.
Okay.
Like you plot in body for the second transfer function, not for the first.
Okay.
Not the original one.
Okay.
It's not reflected there.
You always simplify first?
Hmm?
You always simplify first?
Yes.
Well, I guess that's my question. Do you, what does it mean to plot the Bodhi plot for the simplified version? That's not the...
It's exactly the same. It's just, you're not plotting for simplified, it's just the same. Because it cancels out mathematically, right? So if you cancel out something mathematically, the body plot is absolute value of that transfer function on s equals to j omega, practically, right? So if you cancel it out, s, like j omega plus -2 divided by j omega -2 will be canceled in body plot as well, in absolute value as well, like in phase as well, same thing. So it will not affect anyhow the plot. Plot will be... Yeah, one will go up, one will go down. They cancel out in the sum.
But they might be offset, isn't it?
No. No, this is like pure division. It's like the value is 1. Like x divided by x, no matter what x you use, it's still 1. Okay, so this is a different way to see Rawls-Hurwitz theorem, because this is not how you learn it in control systems typically, and I don't know why. Maybe because people just skip linear algebra, or for whatever other reason, for historical reasons. But Rawls and Hurwitz divide their theorems completely separately, probably like 10 years apart, independently. So Hurwitz had his own theorem on stability, and Rawls had his own theorem on stability, and then we connected into Rawls-Hurwitz criterion, which has nothing to do not to Rawls, not to Hurwitz, which is interesting. So, in my opinion, theorem which was developed by Hurwitz is much easier to use, because if you remember on Rawls-Hurwitz, you're using all of these complicated tables, you put all of the values in the tables, and then you are computing determinants inside, like subdeterminants of tiny parts of the table, and then you compute next line recursively, and you have all kind of formulas for that. Headache, okay? Forget about all of that. We don't need any of it. It's much simpler than that, okay? Much simpler than all of these Rawls tables. And Rawls developed it using these tables, but Hurwitz developed it in a different way. So first of all, for second order degree, the criterion is super simple. All coefficients need to be positive, period. Or they might be negative if you have the first coefficient. So for that type of polynomial, if it is monomial, you do not have the first coefficient, this one and this one should be, not this one, this polynomial, okay? Second order polynomial, quadratic polynomial. Just those two coefficients need to be positive. But if you have third coefficients, they all could have same sign, okay? So they all could be negative, because you always can divide by -1 the entire equation, right? And all of them become positive then. This is the same thing. It's like if you have, for example, minus s squared minus s minus 1, it's completely equivalent equals to 0. Completely equivalent to s squared plus s plus 1, right? You're just multiplying the entire thing by minus 1. So this is stability for second order. All coefficients are of the same sign, period. Third order criteria is a little bit more complex. You have second condition. Still, all coefficients are positive, but multiplication of middle ones is larger than multiplication of the side ones, which means that 1 times a3 should be smaller than a1 times a2 for third order polynomial. This is stability criteria. This is all you need to know, and this is all we will be using in the future in this course. But if you want to go and develop more criteria of that kind instead of all of these tables and so on, you have a very interesting determinant here of that type of matrix. So the matrix is going like that. So coefficients are like every second coefficient. You just write in that as a line. A1, A3, A5, and so on. And until you have the end, the last coefficient, and then you complete that with zeros, whatever number of zeros you need. And then these are all of the even coefficients, okay? So these are odd coefficients, even coefficients. And now you repeat those lines just shifted by 1. Okay, so you're doing exactly the same thing, just completing here 2 zeros, and this goes that way, okay? Same thing, moving by 2 zeros, and then same thing. So shifting by 1, down, shifting by 1, down, shifting by 1, repeating the same thing until you will get to an at this corner. And this is how you know how many zeros you need, okay? Until you get that an here, okay? Last sheet. This will be square matrix. All of the determinants on the main diagonal of any order needs to be positive. This is the criteria for stability, which means determinant of a1 is a1, a1 times a2 minus a0 times a3 is the determinant of second order, should be positive. Then determinant of that submatrix should be positive, determinant of that submatrix needs to be positive, and so on until you get to the full determinant. Needs to be positive. This works for any order, okay? If all of these determinants are positive, your system is stable, asymptotically, okay? This is Hurwitz criterion without Raoult. But in all textbooks that I've seen, I never saw that matrix for whatever reason. And I've seen a lot of textbooks on control systems. Nobody is using that for whatever reason. Any questions? Okay, so what is so special about that left half plane? Like why having poles in left semiplane somehow is important, right? This is the question. Any ideas what is so special about left semiplane specifically? At least for continuous systems and that unit circle for discrete systems. Why they are so special? Let's try to record something on the board. Okay, so let's say you have some differential equation which describes your system. This is linear differential equation of some kind. It could be any differential equation. I'm choosing second order for simplicity. Do you remember how to solve differential equations, linear differential equations from the course on ODE? So what you do, typically you find characteristic polynomial, which looks like that. So you replace every derivative with power of that r, or whatever variable you are using, okay? And then you get r squared, like second derivative, 3r plus 2 equals to 0, so you have that second order polynomial. You find roots of that polynomial, and after you find roots of that polynomial, you write the solution, homogeneous solution of that specific equation when this thing is equal to 0, and this solution will look like some coefficient times exponent to that thing t plus some other coefficient, exponent, negative 2t, and then based on the initial conditions, you choose what these coefficients are somehow, okay? And then you also guess the particular solution, you add that to the homogeneous solution, and this is your total solution of differential equation in general, linear differential equation. This is a technique that you use, and I assume that most of you never even thought to question why you do that thing, right? Like, where it comes from, like what is that thing? Like, why do you need that characteristic polynomial, like how it relates to that entire thing? So the answer is actually very simple. Now when you know Laplace transform, okay, it's just Laplace transform on that thing on both sides. So Laplace transform derivative is multiplication by s. So this needs to be actually s, not r. It's s squared times y, and 3s times y, right, plus 2y. So y you can put out of the parentheses, and you can cancel it. So you don't need it. And then practically you're doing inverse Laplace transform for that polynomial when you get back, okay, to get time domain back. So all of these techniques that you learn in differential equations are coming from Laplace transform. And since people do not learn Laplace transform when they learn ODE, people just, like teachers give you that equation, characteristic polynomial, whatever, from the sky, you know. So this is the reason that you have that thing. But what I want to concentrate on is that thing. So for any differential equation that you might have, your solution y of t, whatever the output is, okay, this is what you want to find, will look like c1 times exponent to some, let's say, we still will call it s1, let's say, s1t plus c2, some constant s2t, and depends on the order of the system, you'll have more of terms of that kind, okay? This is generic solution of any homogeneous linear equation, right? But what is that thing? So S1 is root of that characteristic polynomial, could be complex or could be real, right? So let's see. So let's say you have S1 equals alpha plus beta j, some complex number, whatever it is. So beta might be 0, and then it will be real, or it might be something, and then it will not be real, it will be a complex number, all right? So let's see what that thing is. So C1 times exponent of alpha plus beta j times t. You can write as C1 exponent to the alpha t, exponent to j beta t. Multiplication of two exponents. So multiplication of two exponents is the exponent of the sum. Good so far? Okay. So let's see what that value is. So this is that real part, and this is imaginary part. Remember Euler theorem on this one? This is cosine plus sine times j, right? So what does it mean to diverge? This means that magnitude of that output y will go to infinity. So we need to compute absolute value of that thing to know the magnitude of that term. Like, is it going to infinity or it's not going to infinity? So what would be the absolute value of that thing? It will be absolute value of C1. Absolute value of multiplication is obviously multiplication of absolute values, right? And then you'll have e to the alpha t. And then you'll have e to the j beta t. But what is that thing? This is 1. So this is C1 times absolute value of e to the alpha t. But alpha is real part of our root, right? So how this function might look like? So if alpha is positive, how this thing looks like? This exponent of 5t, for example. How does it look like? It looks like that, right? This is how exponent looks like when the coefficient is positive. When it is negative, how does it look like? The other way around. So what is the condition that this thing will not go that way or that way, but will go to 0? That this thing is negative, right? And this is exactly the condition. So this thing needs to be negative. And then all of these exponents, like if each one of these exponents will be this negative real part, the sum of the exponents also will converge to 0, right? This is the reason why it needs to be negative. Real part of S needs to be negative. If alpha is positive, it's diverging, so it's unstable. And it's enough that even one of them will be positive, right? So if you add in something which is converging to 0, and you have many terms which are converging to 0, but one of them is diverging, the sum will diverge. It's enough that one of them will be unstable in that sense, which is positive, sum will diverge. Because here, this is basically sum of them, right? Sum of that type of terms. Now, what happens here is that you can learn from that additional thing, very important thing. So you have sum of these exponents. And let's say the system is stable, so all of them look like that. So all of them diverging from different sides. One is slower, one is faster. You have all kind of sort of super slow, whatever. But they all converge to 0. Which one of them will decide how fast the entire sum is converging to 0? So you're adding, like, your output y will look like sum of all of these functions. So which function is the most important here to understand the slowness of convergence? The slowest one. Yeah, the closest to 0, alpha. The smallest alpha, because this is that thing, right? Because some will be, like all of them will already converge. It will be 0 here for most of them, but this still will be imposing some value which is not 0, right? So the slowest ones are the most important ones in the response, because everything else converges to 0 already. You don't care about them. And this is what brings us to the theory of dominant poles, which you hopefully also heard about in Controls 1 theory, in the first course on classical controls, where we're using the rightmost 2 poles or single pole as dominant poles, most important poles, which are imposing how system will converge, how fast it will converge, settling time and all of these things, right? How fast it will settle. Because of that. Because the slowest one in the sum will be dominant one. It will tell you how fast you can converge. So if all of them are very fast, then it converges faster. But you need to look only on the slowest ones. So if you know the slowest one or 2 slowest ones, this will tell you how fast your system is converging. All right? Any questions? And this is practically, I almost answered that question. Like, what will happen if they are to the left to a particular point and the real part becoming more and more negative? What will happen? The system will become faster. It will respond faster. So if all poles are behind some particular line, the system is faster. And this is how we can draw it, okay? This is how we can connect performance of the system to location of the roots, of the poles, in that case, okay? So farther you go that way, to the left, faster your system becomes, which means your settling time becomes shorter, okay? It becomes faster. So this is step response, for example. And you have some overshoot, you have some settling time, which is how fast it gets into that plus minus 2% from the final value result. And then you have also rise time and other things. So your rise time will be shorter. Your settling time will be shorter when your poles are getting farther and farther to the left. But if you get too far to the left, you're technically increasing bandwidth of your system, which means it starts to become more sensitive to noises and disturbances. So you want that system to be fast, but not too fast. Because if you introduce some fast dynamics into system and allowing the system to behave very fast, then it's much more sensitive to noises, because your bandwidth of the system becomes wider, right? Now, that angle of that thing is overshoot. And you have formulas connecting the dominant poles from that function to particular angle phi. And larger the angle is, higher the overshoot is, or stronger the resonance is. So all the things are connected. So it's more oscillatory behavior if it becomes more complex, okay, farther into the complex domain, which means bigger angle of phi. And this defines some sort of trapezoid in the complex domain where you want your poles to be located. Okay, so if poles are located inside of that trapezoid, then you get both stability and performance, which means settling time, overshoot, rise time, and other things that people typically like in control systems. So from now on, we will discuss only particular locations of the poles or regions for locations of the poles, because we can translate them into actual performance and stability. And if it will be discrete time system, it will be that thing will be inside the unit circle, sub part of unit circle somewhere. Okay, so you'll want to locate that in unit circle somewhere for stability. Any questions? Okay, so how can you model any linear systems? And we go fast through that because we will not really use it, except maybe in the description of the project itself. But you have multiple different ways to estimate parameters of the system. You have that black box, motor or whatever it is. You want to know what transfer function that thing has. So how can you do that? So number one, if you have stable open loop and you have second order, and you want second order approximation model for your system, which means dominant pole approximation for your system, what you can do, you can just input step, okay? And then you will get some sort of function like that, right? So you'll have the blue type of response, step response. You can measure the value of the overshoot. You can measure the value of the settling time. And based on these two formulas, you actually can compute these parameters back, which means this will give you this transfer function just from step response. So you can use step response of any unknown function to estimate second order model, which will give you that omega, zeta, and this is all you need to describe the system with two parameters. Okay, because you can measure settling time and overshoot. Now, additional approach is using Bode diagram. This is also only for stable systems in open loop, and it's advisable that your zeros and poles will be sparse enough, which you obviously don't know where they are, but you assume that they are sparse enough, which means they're not close, not close to each other. Otherwise, they can interfere with each other somehow and create some weird artifacts. So in Bode diagram, you just send in sinusoidal wave as input and sweeping all of the frequencies and measuring response, which must be also sinusoidal, because for all LTI systems, sinusoidal inputs causing sinusoidal outputs. Okay? We can prove it, I will not, but hopefully you've seen that in Signals and Systems or maybe somewhere else, that for any LTI system, sinusoidal input is eigenfunction of the system, which means it produces also sinusoidal output. Different phase and different amplitude, this is the only difference. Now, given that phase and amplitude, you can plot Bode diagram as a function of frequency. So sweeping the frequencies as input, measuring frequencies as output, and all of their amplitudes and phase changes from the input. And this is exactly what Bode diagram is. The ratio of amplitudes, input and output, and difference in phases between input and output. Okay, this is two plots of Bode diagram. Now, given Bode diagram, you can estimate back the transfer function. Because you know, like if it is going up, it's zero, going down, it's pole, things of that kind, okay? So you have all of these pairs of poles and zeros. So this is second way to estimate it. And third typical way or classical way to estimate it is just from physics. So you know properties of the system, you know mechanical properties, electrical properties. chemical properties, whatever they are. You just build your system based on your knowledge of physics for your mechanical system or electrical system or whatever the system is, okay? And I understand this will not be useful for brain estimation, but for many mechanical things that we know how they work, we actually can use that technology to identify actual transfer functions. So what happens with nonlinear models? Because they are very different from linear models, obviously. First of all, step response and Bode diagrams in nonlinear systems dependent on input, which makes them very hard to work with, okay? So your Bode diagram will depend on what input you send. For different inputs, you'll have different Bode diagrams, different frequency responses practically, right? Same thing with step. Superposition is not working anymore for nonlinear systems. So you cannot use that assumptions that you can build signals from smaller deltas and other nice stuff like that. Transfer functions practically have no meaning in nonlinear systems because transfer functions are a reflection of ordinary differential equations, and you do not have ordinary linear differential equations anymore, okay? The equations are nonlinear, so you can approximate them with linear, but this is not the same thing. And all systems have uncertainty in parameters, which we ignored so far, and this is robust control theory which solves that problem, okay? How to deal with uncertainty in parameters where you don't know the parameters exactly, and you cannot even assume that they are known. Any questions? Okay, so here is physical modeling, as I promised. This is the easiest one, and I will not go through the physics. It's just, you have list of equations for torque, second Newton's law, you have back EMF, Kirchhoff law, all of the electrical and mechanical stuff. You have just list of equations. Each one describes that torque is proportional to current that you send to the motor, DC motor. You have second Newton's law, which is proportional to MA equals to F type of stuff, but for rotational part. Okay, you have back EMF, which is returned back from the motor. So it's related also proportional to the change in the angle, and theta is angle of the motor. And this is what I want to control. I want to control theta of t with some particular controller, right? And this is just sum of the voltages in the loop equal to 0, which is Kirchhoff law, okay? As electrical engineers, I hope you remember something like that. We will not use it much, okay? Don't worry if you don't remember any of these things. You don't need to, just examples that you can describe the system as those two differential equations, all right? Now I want to get rid of the back EMF part. I want to get rid of other, like torque part, and so on. So out of those 4 equations, I want to build 2 equations, and this is how it will look like, just algebra, okay? I just substituting that E here, and here I am substituting that T into that second equation, okay? Getting 2 differential equations as a function of I, which is current that I'm giving here, that current which is flowing here, okay? And angle of the motor. They connect current and angle of the motor, okay? And then I have also input voltage. This is what I have. Now, essentially, I want to bring these 2 differential equations into one differential equation of higher order, because I want something which connects V to theta, right? This is the equations that I want, which describes that entire system. So I want to blend these 2 equations somehow in such a way that I will have one equation of 3rd order, but this equation will not include I, because I do not have anything with I here, right? It's just current which flows. So I know it exists, but I'm not measuring that directly or not providing it directly. So from these 2 equations, I want also to find transfer function of that motor system, okay? Which connects, again, input V to the output theta. So the output will be theta, this is our Y of S, and our input, which we typically write as U of S, will be V, which is Laplace transform of voltage, input voltage. And it could be any voltage, any shape, any form, okay? So this is what we want to find. How we do that? Just reminders that Laplace of derivative is multiplication by S minus initial conditions. Second derivative is S squared multiplied by the same thing. So I will do practically Laplace transform on both sides of that equation. and on that equation as well. Okay, so this is what we get. So first equation will be j times s squared, because this is second derivative, times theta of s, which is Laplace transform of theta, minus that thing and minus that thing. Okay, equals k times Laplace transform of I. So I did Laplace transform on both sides. All right. Same thing with that equation, and I get some other complex equation. You don't need to go into details. This is just algebra practically. You're replacing every derivative with multiplication by s. Two derivatives with s squared. That's it. This is the algebra. So practically copying that entire thing. Now I need to solve that system of two equations algebraically. This is algebraic equations, right? You do not have any derivatives. This is constant actually. So this is not really derivative. This is some number. So pay attention that all of the smaller things, it's a function of time, which means that theta of 0 is number, and theta dot of 0 is derivative at time 0, which is also number. Okay, it's not derivative really. There is no t here. Okay, it's just number. So all of this and this, it's just numbers. So don't worry about that derivative. Everything else is just solving system of two algebraic equations, and you need to find g of s from that. So let's write theta s as a function of v of s, solving these two equations, and this is what you will get. You will get some first term plus some complicated second term, but you want to find theta divided by v, and here you do not have v at all in that second term. So it's like theta equals alpha times v plus beta, right? So this is what you have. You have your theta equals alpha times, same thing, alpha times v, both of them are functions of s, plus beta. So alpha and beta are some constants, some numbers. I want theta divided by v. Can you compute them as a function of alpha and beta? Regardless of what they are. Like, can you write that thing which will not be dependent on s? Will not be dependent on v or theta. So that side should not depend not on this one and not on this one. So can you algebraically manipulate that thing somehow that you will get that thing not dependent only on alpha and beta? The answer is no way you can manipulate it that way, okay? You cannot write that transfer function as a function of alpha and beta. There is no way unless this thing is 0. And then this will become just alpha. Right? This is the only way. Now, how can you make this thing 0? How can you make that right side 0? This becomes 0 only when all initial conditions are 0, which means theta 0 equals to 0, theta of 0 equals to 0, theta dot of 0 equals to 0, I 0 equals to 0, all of them 0. Only then that entire thing will be 0. Okay? This is exactly what I was talking about when telling you that transfer functions defined only for initial conditions 0. Because otherwise you cannot even define them for initial conditions which are not 0. It makes no sense. You cannot actually write that ratio as a function of other things. Okay? This means that this is your transfer function. Okay? And that right side, all 0. That's for 0 initial conditions. This is the only way to define transfer functions. Questions? Yes.
Would it have been any different, right, if you defined IMT to be j double dot theta double dot over k, and then you substituted all that in, so then you didn't have anything dependent on I on the left side of the bottom equation?
Not sure that I've got the question.
So if you substitute like an IMT from the, so if you move k over, right, you have IMT equals stuff, then you take the derivative of that with L, R,
yes.
and IMT. So then everything.
So you get third degree differential equation, yes.
Right. So like, would that
We will get to that. This will be the same.
Okay.
Yes.
So you still would have had some constant that you would have had over it.
Yeah. Okay, so this is how you convert from transfer function to OD, and we will get to that exact equation that you are talking about. Third order differential equation. So now we have that transfer function. which was here, right? That transfer function. Now, let's say I'm giving you transfer function and asking you how can you get back to differential equation. So it's very simple, actually, procedure. So you know that your transfer function, which is output divided by input, has some polynomial here and another polynomial there, right? So it's numerator, denominator polynomial. So you can cross multiply them and make inverse Laplace transform on both sides. So it's inverse Laplace transform of dy equal to inverse Laplace transform of nu. So let's try that, right? So I'm doing multiplying this one by theta and this one by v, right? So you'll have kv on one side and this one times theta on the other side. Now pay attention that now we go the other direction. Multiplication by s is derivative. So multiplication by s cubed is third derivative, right? Third order derivative. So that's what I'm doing. I'm doing that as operator on theta. So it's L times J times third derivative of whatever that thing is, which is theta. And you'll get that thing in time, okay? Same thing, second derivative of theta times Rj plus first derivative of theta times k squared. This is what you see here. And on that thing, this is constant, so it's nothing. It's same constant times inverse Laplace transform of v is small v of t. This is the equation. And we started with these two equations. So is it equivalent? So are these two equations equivalent to that higher order differential equation? You don't need to compute here anything. It's just generic question. You don't need to convert this two into this one. You can. I mean, it's actually very simple. I mean, all you need to do is just to put to make one more derivative here, and then you'll get that equation exactly. Okay, so you're just making dot here is j theta 3 dots k I dot, and you're replacing that I dot here with j theta 3 dots. Practically speaking, this is what you'll get, and you're replacing also I with j divided by k theta 2 dots, right? Because this is I that you need to replace here, and you'll get exactly the same equation. So they are equivalent. And now, reminder question. Now, we got exactly the same thing, right? We got that from transfer function, we got exactly the same equation. So are ODE and transfer function representations equivalent? Okay, I need to move that part from here. They are not, because we completely ignore initial conditions here. Equation will be exactly the same equation. Okay, you can get exactly the same equation, but you are assuming initial conditions 0. So they are not. Okay, you have different initial conditions. And now we move to starting with state space representations, which is the main topic of this course. And I will just start talking a little bit about that, assuming that you remember a little bit of linear algebra. And next time we will talk mainly about linear algebra related to all of the things. So I will remind you how to manipulate and operate matrices and vectors and eigenvalues and other things of that kind. Maybe I will record even lecture, which is helpful to refresh your memory on linear algebra if you don't remember any of these topics, so you'll be able to get back to that and to watch actual videos. And I will jump from one topic to another fast because we do not have much time for linear algebra, and it's a huge topic, many different subtopics. But now I will just give you some brief overview what that thing is and why we talk about that. All right. So what is state variable? State variable, it's smallest subset of variables that describes the entire system at particular time t. Which means you can find all kind of voltages, currents, forces, whatever it is, whatever you can measure or see, or sometimes you cannot measure. And these are variables which are describing your entire system. This is very abstract definition, okay? We will get to details later, but in general, state variables is everything you need to know about your system. So if I give you state variables, you can compute everything else from the state variables. This is just enough variables to compute everything about your system that you would ever want to know about it for that particular time. Okay? If I give you state variables at a particular time, you can compute everything about your system. Now, state space is all possible state variable values, which means they can take different values, typically numerical values. And this is all possible values that you could get. So it's similar to probability, where we have probability state and probability space. Similar here. It's like all values that it could take. This is what we call state space. Essentially, what that is, if you go deeper in understanding of what is going on, it's just mathematical trick, really. You just seen that you can write one single differential equation of third order as differential equation of second order and first order. Similarly, you can write any differential equation as system of n differential equations of first order. Which means if you have differential equation of nth order, some big complex linear differential equation of nth order, you always can write it as n differential equations of first order. So you'll have system of differential equations. Each one of them will be first order. How to get there? This is a tricky question. We will learn about that. But this is just mathematical trick, how to represent the same single big equation as system of smaller equations, simpler equations. These are state space equations. That's it. Practically, this is just mathematical trick to convert your regular differential equation into system of equations. Sometimes people even learn it in differential equations when they have systems of differential equations to solve, right? Have you seen that in any courses where you have system of differential equations instead of one, and you solve them simultaneously? There's all kind of Wronskians, other stuff. You have Wronskians, or like Wronskian is like determinant of some matrix. You have all kind of, but here we will not use any of it. It's just my fading memory from 20 years ago when I learned differential equations. I remember all of these crazy names. I don't remember what that is, but I remember the name. All right. So, not always state space variables have particular physical meaning, which means that sometimes it's like ratio of air incoming into engine divided by current coming to some motor, whatever. It could be all kind of weird things that you cannot even measure, you cannot see them, you cannot do anything about them. They're hidden variables. And actually you will see a lot of that kind of stuff in machine learning, you will see a lot of that kind of stuff in computer vision, and in other areas where people are using hidden states, hidden Markovian systems. This is very similar, same type of systems actually. They are also state space in a way. So you can use state space in any of these areas as well. And Kalman filters are used there as well. So you have all of the same ideas, where you're trying to describe your system with minimal set of parameters of some kind. And then you try to connect them through some differential equations. It means some dynamics that you have in the system. But typically it's easier to pick some variables like current, angle, velocity, or whatever, okay? And using these parameters and their derivatives as well. Now, unfortunately, with state space systems, we cannot use, or maybe fortunately, I'm not sure, we cannot use serial controllers or feedback controllers as usual, like block diagrams that you used to see controller times your plant, and then you have forward loop, and then you're closing that with negative loop. We need different structures here. We need different type of connections here for state variables and for state controllers. But they will be much, much, much easier to design because it will be like one line in MATLAB. No black magic anymore. Previously, if you remember how to design controllers in classical theory, it's like trial and error, more or less. You're trying something, then it doesn't work, then you tweak the parameters a little bit, trying again, simulating, and doing that for a few hours, and then maybe you're lucky and it's somehow close enough to what you wanted. Not here. one line of MATLAB code. That's it. You're done with controller design. One line of MATLAB code, magically almost the same line. You need to make only two transposes somewhere, and you get estimator of the state. Another line, you get Kalman filter. It's just that simple, okay? Compared to classical theory where it's all kind of black art of some kind, where you need to design something. Yes?
So are you saying if you put it in state space representation, you can't use the nice diagrams that we were showing last week?
Not that type of diagrams. Yes, it still will be controller in the loop as negative feedback, but the controller will be connected to state instead of the output. So output will be separate from the state. State will be state, then you get multiplication by some matrix, and then you get output. But controller connects to the state, not to the output. But to connect it to the output, you need observer, which is separate part of that course. And we will learn how to estimate the output and how to estimate the state from the output and input. It's possible in some cases, not always. But we will learn conditions where you actually can do and convert it into regular classical control and controllers, okay? Regular negative feedback loop. It's doable, all right? Now, first of all, this is very good to learn about state space because it's completely equivalent to ODE. You have initial conditions, you have everything which is related to the original differential equation. So you are not losing any information. Now, we can get exactly the same analysis for CISO systems, which is single input, single output systems, one input, one output, and multiple inputs, multiple output systems, which is more natural to work with in reality, right? You don't have many CISO systems. Most of the systems have multiple inputs and multiple outputs. Same theory. We will not work much on it, but theory is exactly the same. Same formulas, same code, same everything. Just CISO systems easier to handle, okay? Now, we have almost same analysis for discrete time and continuous time systems, which is very convenient. So it doesn't matter if your system is sampled, like computer, and your algorithm is running in the computer, your controller is practically computer and not analog circuit, okay? Or it is actual analog circuit, which is continuous time control. Exactly the same theory. You just replace S by Z variable, Z transform instead of Laplace transform. Everything else more or less the same, okay? You have like only stability differences. So instead of locating poles in the left semiplane, you locate them inside unit circle. This is the difference, okay? That's it. Everything else the same. We can relocate poles anywhere we want, which means you tell me where you want your poles to be in closed loop, which will identify your performance and stability and everything you need from your system, right? Again, I will give you a single line of code in MATLAB, which puts it there exactly in these places, wherever you want them. Looks like magic. After course controls 1, okay? And all of the robust control is also based on the theory of state space. So all of the more modern theories of control that you will see in development right now, in research and so on, and also parts of nonlinear controls are all based on that. And believe it or not, but all of the theory from 60s through 80s, you still have all of these controllers everywhere in hardware. Airplanes and other places, they are using that type of controls, okay? So if you go to industry working with controllers, this is what they will be most likely doing. Not robust control, not nonlinear, that type of control, okay? This is the most popular type of control still everywhere in industry. So it's not the modern control in our sense, okay? It's not super modern theory, but it's very established. As I said, you have also extensions to nonlinear control from that theory, all right? So how can you convert back from ODE to state space? This is actually a tricky question, and we'll spend some time on that in one of the future lectures. But it's not that easy, okay? Somebody needs to define your variable. Sometimes it's possible to to write system of equations from a single equation easily, and sometimes it's very complex and very difficult to do, okay? So somebody needs to give you like how I identify or define the variables. x1, x2, x3, these are state variables, and we will always write them as column vector, x1, x2, x3, and so on. Depends on the order of the system, and order of the system will be n, okay? And our system of equations we will write that way. We will get to that later when I talk about linear algebra and so on. But think about that as vector of derivatives. First derivatives is like x1 derivative, x2 derivative, x3 derivative, vector of derivatives of the state, equals some matrix A times that vector x, which is column vector x1, x2, x3, plus some matrix or vector B, some constant coefficients, times input u, and this is our system, okay? This is how we will describe all of the systems, which is practically first order system of first order differential equations, okay? You have n differential equations of first order, and all of them are linear. And the output will be computed as some matrix C times that state x, plus some matrix D times inputs u, okay? This will always be our linear state space system representation. I'm just showing that right now, that you will get used to that because we will be using that every single lecture, okay? Like I will just tell you like A, B, C, D. I will not even write that system. I'll just tell you continuous time or discrete time and A, B, C, D matrices. This is all you need to know. It always will be of that kind. For discrete systems, it's a little bit different. For discrete systems, instead of derivative, you have xn plus 1, which is the next state vector, equals matrix A times present state vector, x, okay, all of the values that you have right now, plus B times inputs u. And n is kind of time index, but it's like 1, 2, 3, 4, 5 instead of t, right? And yn, same thing, c times x plus d times u. Sometimes people write in that index as just rectangular parentheses, like brackets, okay? Same thing. So you'll have textbooks which are using index, like subscript, and some are using rectangular brackets for the same thing, okay? Any questions so far? Okay, so this is just example how you convert back, and probably this will be the last thing that we'll do today. How you convert back these equations into state space somehow, okay? So how can you convert that into state space? And I defined for you already the variables. So first variable will be I, second variable will be theta, obviously we are interested in them. X3 will be theta dot, which is angular velocity, like how fast that thing is changing the angle, all right? So how we do that? We need to write x dot as a function of other x's and u. This is our goal in converting it into state space. Into state space equations, you have only variables x, x1, 2, 3, 4, 5, and so on, and u. That's it. And y, obviously, right, for the output. So this is everything that you want to leave. So you want to kick out all of the thetas, i's, u's, other like voltages, v's, and so on. Everything which is not supposed to be in these equations. So here's how you do that. You compute in first derivative of x1. So x1 is I, so it's I dot. We know that I dot is that thing minus that thing divided by L, right? This is from that differential equation. So this is what I write here. It's like 1 over L times the rest of the equation here. Now I want to get rid of all of these things. But what are these things? So V is practically U. This is our input, right, of the system. I is x1, so I replace it with x1. And theta dot is x3, by definition. So I replaced all of these variables with variables that I need to keep. So now it is state space equation. So x1 dot equals 1. So you have u here, x1, and x3. You do not have any other variables, so it's fine. x2 dot is theta dot. So theta dot is x3 by definition, right? So got the second equation. x3 dot is theta 2 dots, so I can use that equation. right? So it's k divided by j times I, but I is x1. So it's k x1 divided by j. So I've got 3 state space equations. All of them are function of x1, x2, x3. All right? And u. Y is equal to theta, because this is the angle that I want to control. So it's by definition x2. So I wrote y as a function of x2. You can write all of the same equations as a matrices, right? So this is just, I'm copying coefficients here. So in the first equation, you have minus r divided by L. So this is first coefficient. Nothing multiplies x2, so it's 0. And then minus k divided by L multiplies x3 here, right? It's just algebra. We will get back to that, how you do that. But luckily, we don't really need to do that in that course because there are much easier ways. I'm showing that type of way just for you to be aware how difficult that might be if you do not have any standard ways of doing that. Converting ODE into state space, it looks very tricky and difficult. But we will learn specific techniques converting it into matrices directly from the equation coefficients. Okay, you have multiple ways to describe it. And you have even multiple state space descriptions, depends on how you define the variables. Okay, and y will be just 0 times x1 plus 1 times x2 plus 0 times x3. So it's like 0, 1, 0, x times 0 times u. So you do not have any u here in that equation. Okay, done with it. So this is how you convert ODE into state space. Any questions? Yes.
It's only, so you're saying that there could be an equivalent representation.
Mhm.
So like we could have had an x4 that was I dot, and then you would have had.
No, you cannot have x4. The system is third order, so you need 3 variables.
Well then,
But you can, for example, switch x1 and x3 as example. You switch x1 and x3. You define x1 as theta dot and x3 as I.
Well, no, yeah,
You'll have
like-
completely different system, right? You will have.
Why wouldn't you have I dot? Is really what I'm trying to get at. As we-
You might define something as I dot and then to have some other variables. Yeah, and sometimes it works and sometimes it's not. Depends on how you define it.
Okay.
So you can define it in the right way or in the wrong way that you will not be able to get out of it. And this is the issue here, that if you just try by trial and error, it's too difficult to guess how you need to define the axis.
Right.
So you have standard ways to define them, which always work. Okay?
Wonderful. I'm good.
Okay? Thank you.